different network conditions in a PLC network. Okay, how can we model a power line communications network? We consider only the access network, that is the network from the transformer, from the medium voltage to the low voltage network. This here is a symbol of the transformer. For communication purposes, this is also what we can call the base station. And typically, the wiring of the power cables from the transformer nearby your home is in certain trunks. And these trunks distribute typically in a tree-like fashion along the roads, and then you have short links to the home, to the house, and of course inside the house there is a similar fork type or tree type network. This this graph sketches only the distribution network from the transformer medium voltage to low voltage to the houses. And in a typical area, let's say not the most densely populated area in the city with high-rise buildings, let's assume that we have a suburb situation where there are individual private homes, then the distribution network may look like this. So there is some feeding cable, and there is, for instance, a small street with 3 houses. There are other streets, and there are these types of streets, and so on. And as a typical example, in Germany, for instance, and many other countries, one of these transformers typically feeds about 250 to 400 houses or subscribers. There are a number of sections or trunks, and per trunk there are typically these numbers of users or households or houses per section. Logically, the power line is a bus, a multi-access bus or a logical bus. That means we could also transform this topography into a logical topology where here the wide area communications network is connected inside the transformer compartment, and on the low voltage level there are many of these houses in having different distances from the transformer to each of these houses. So if we would have no signal attenuation on this link, we could deal this bus as a typical local area network with a length of, well, the typical length in a rural, in a suburb area is up to 500 or even 1,000 meters. Typically it's shorter. So if the communication attenuation is small, then we can use the mechanics we are used to implement and to run in standard local area networks. So there is a strong similarity. Unfortunately, the attenuation along this link can be quite high because, again, the power line has not been made for communications purposes. So it is a low impedance link, but having quite a high attenuation for frequencies, for instance, in the megahertz range. And this is one of an example which Mr. Modrzejewski has used in his PhD dissertation. So this is an example, a power network, where here we have 2 transformers, here and here, access points where the transformers are located, and then we have feeding points, and the customers, the houses, are these I are the typical standards. I should also explain that typically a power distribution network is designed such that in the case of a power outage, let's say a cable is broken, for instance, let's assume that this cable here is broken, then we cannot feed the typical way, but there is a connector or a switch at the end point, and if you close the switch, then you can feed the house here over this way from here. So typically the low voltage network in city and suburban areas is a ring, which is usually open, but in the case of failure it is closing or even closing automatically, so there is no outage if we have just one link failure. And this is a typical example which we have been using in one of our research projects, and also it has been used by Mr. Modriewski. Okay, again the same situation. The transformer, the wide area access base station, and having, for instance, a first feeder link, then going further into this street, having a split connection, and going this street, there's another street, and so on. So in total, the distance from here to here is eventually a bit too long with respect to the signal attenuation of the high frequency signals on the power line. That is why we can use so-called repeaters. A repeater, well, as the word says, repeats the signal. In the case of power line communications, if we can receive the signal here and we want to retransmit it in this direction, this does not work, because the power line is a power line. The power line cannot distinguish between two directions. So if we want to feed in a signal here and we have received a signal from here, the signal must be transmitted in another range, either on the time domain or on the frequency domain. Here I assume that we are using frequency division multiple access. That means we have a frequency range of different types, modulation we will discuss later, a frequency F1, which is used only from the base station to the first repeater, and then we forward the repeated signal with frequency F2. In this case it feeds this street and it feeds this area until we eventually have a next repeater, and this next repeater goes to another frequency area F3, and for the most distant house we might even need another repeater. That means if we do use different frequencies, in this case 4, our bandwidth which we can use is divided by 4, because we have 3 repeaters, F1 here, F2 here, F3 here, F4 here. If there is a strong attenuation, and definitely the attenuation from here to here over this long distance is eventually so strong that we can't hear the signal F1. We hear the signal F1 at this repeater only with a so low level that we can neglect it. So eventually we can reuse F1 for this last segment. And this is one of the design topics, which is of course also important in other communication networks, also in mobile communications. So the power line signal transmission characteristics are as follows. We do have quite a high attenuation for high-frequency signals. Later at the end you will find references. For instance, there is a very recent book where there is a complete chapter on the attenuation topics of PLC signals. What we also have noise signals, and I will come to this soon. We also may have signal reflections, and definitely we have changing characteristic impedance. As I mentioned already, if you switch on and switch off power consumers, if you switch on a heating, then definitely the impedance goes lower, and if you switch it off, the impedance can go back to a higher value. And of course your communication system, the transmitter and the receiver, must be able to cope with this. Also, there might be multipass propagation. So if we, as I said here, there are these so-called switches. These switches are usually open, but nevertheless you can understand this as a kind of small condensator. So there is some capacity, and high frequencies can be transferred via capacitors. That means that there might be some communication even over here, and that means there is a signal which is going this way, and there is a signal which is going over this way, and that is multipass, which we know very well and understand quite well from mobile communications. Also, frequency selective fading can occur. If there are signal reflections, this means that there are standing waves, and standing waves always produce frequency selective fading. And finally, due to a higher attenuation, you might have bit failures, bit error rate. There is a so-called bit error ratio. Packets are a couple of bits, and in the end there might be losses of data packets, and we have to cope with this. So, to summarize, PLC transmission characteristics, a PLC network, the same one which I sketched already, can either be disturbed by power appliances, for instance any electronic system, a TV receiver for instance, or a washing machine, produces noise on the power line, produces impedance variations due to switching on and switching off these appliances, and the appliance can also produce high frequency noise. For instance, the fan in your hair dryer has typically quite a cheap electric motor, and this quite cheap electric motor produces a lot of brush fire, and that means this is noise, even high power noise. So one of these things running can disturb the performance of a PLC network. Also, there are radio transmitters, and if the radio transmitter transmits in an area where we do our modulation frequencies use on the power line, then this can disturb as well. The crane here is a high power consumer, again another consumer, and other PLC networks can disturb the behavior of a neighbor PLC network. So for PLC, the so-called electromagnetic compatibility is of prior importance. PLC systems, broadband PLC systems, may operate up to 85 megahertz. So they cover a range from 2 to 85 megahertz eventually. And in between there are a number of commercial or private frequency bands. For instance, the radio amateurs have their reserved shortwave frequency bands. There are other public radio frequency bands in it. So we have to take care of this, and I will show you how to do this. Also, the PLC networks produce their own radiation and can cause disturbances for other surfaces, for instance, shortwave radio. And they may also be disturbed by high power radio transmitters. In order that they do not produce too much own radiation, they usually work with a quite limited signal power. This also means that the PLC modems do not consume too much electric power. So the received signal is typically received in the noise floor of the background noise. That means we have to design these modems very carefully. Okay, how to deal with all these problems? What are the countermeasures? We have to use a very robust modulation scheme. And in the recent times, there have been two developments triggered by the advent of modern mobile communications. One is the so-called spread spectrum technology, which, for instance, has been used in UMTS, the 3G mobile communications, and most modern systems now are running OFDM, orthogonal frequency division multiplex. These two mechanisms, you have learned how they work in the communications lecture, so I don't have time to go into this. But what is important, as I showed you, the PLC network is a bus network. That means we have to organize the medium access. The so-called medium access control layer has to be designed carefully. Of course, the goal is to provide a maximum network utilization, but also we do need efficiency for all services, fairness for all services, and giving the quality of service for various services, different quality of service requirements for different services. So we must be able to do this, otherwise we won't have acceptance of the technology, and we must be able to be competitive with other access technologies in the world. And as usual in a communications network on a channel which may have errors, we have to install an error handling mechanism. So finally, some classification. PLC can be classified from the frequency bands used. The first implementations of PLC were broadband PLC networks, nowadays running the frequency band I mentioned already. They are usually designed for distances, smaller distances. Nowadays, I would say, from our experience and measurements we have done, even 1,000 meters nowadays possible. They have been more expensive in the past. Nowadays, the the integration in the chips has progressed a lot. So even they are not longer more expensive, and they can provide file layer speeds of nowadays even much more than 1 gigabit per second. On the other hand, narrowband PLC is designed in a very low frequency range, in a frequency range which is below the long wave radio transmission frequency. So the long wave range, the long wave radio band starts at 150 kilohertz, and this is running below this. Due to the lower frequency, the attenuation is lower. That's why we were saying in the past we can cover longer distances, and we can do this at lower cost, at least with simple modulation schemes. The speed definitely is lower. For smart grids, as I mentioned already, at least for the commands, we do need a very low delay. And this is difficult to deal or to manage with narrowband PLC. We do need a high coverage. In this case, narrowband PLC has its advantages. We have to implement a low packet error ratio or a low packet error rate. Well, if we have enough speed, then we can implement this with higher redundancy. So this is perhaps better be done with broadband PLC. I skip more or less this complex slide. As I mentioned, standardization took quite a long time, and there are many proposals for technologies of PLC. In the end, most of them did vanish, and nowadays we have only few standards which are really of technical importance or implementational importance. For narrowband PLC, still Prime, this is a Spanish design, is existing because it's now part of the G3 standard. And in broadband PLC, we did have standardization. The first standard was IEEE 1901, and it is now superseded and extended by the ITU G.HN standard. And all modern systems now are running OFDM. One of the earlier systems here, for instance, the Yitran implementation was running with spread spectrum techniques. So, again, I mentioned this already, this lecture focuses on access networks. So we are talking for smart grids on PLC in low voltage area, in low voltage networks. We are transferring data. We have the standard OSI ISO layer structure. This holds also for PLC. The only difference is that from the IP, nowadays IPv6 standard, to the network layer, in between there is typically an adaptation layer to adapt to some special requirements of PLC. The PLC network layer is a bit different from the network layer of a classical cabled, for instance, LAN architecture, and below as well. But the architecture in principle is according to the OSI layer structure. Again, the example which we have seen already, and due to the kind how PLC developed, we have also a synonymous naming of PLC. A couple of promoters of PLC did mention or name it DLC distribution line communications. Well, because it is the access line on the low voltage area. So DLC and PLC means the same situation. So, for instance, if you have a bus, then you have, in this example, 6 nodes. The distance from the access node to node number 6 might be too long, that you have eventually to run a repeater. In this case, we have just one repeater. The node number 4 is also the repeater for node number 5 and node number 6, whereas nodes from 1 to 4 can be reached directly. Yeah, as I mentioned already, the power line communication channel is varying over time. Varying over time due to noise, to impedance changes and so on. That means if you have, let's say, 2, or in this case 3 wide area network interconnections, access nodes, all of them are, let's say in brackets, are connected to the internet, but there might be failures. So this one might be disconnected for some time, the other one and the third one as well. And in this case, we must be able to do an automatic rerouting from the internet connection to these access nodes, that if, for instance, this connection fails, we must be able to feed via this way or via this way. And this has to be done automatically, and that means this must be implemented in a PLC system. Okay, so we have used already half of the time. I will make a short break here, and in the second half of this lecture we will focus a bit more on this current G.HN standard, in order how to describe what are the topics and how can we implement it a high-performance PLC connection. Okay, thank you. Relax a moment and then we start with